Welcome back. In this next section, we'll discuss Syn dihydroxylation. So just like with anti-dihydroxylation, in this reaction, we're adding OH and OH across a double bond. But in this case, we get Syn stereochemistry. So for this reaction, the reagent is osmium tetraoxide. Okay, and so this osmium tetraoxide adds to the double bond in a concerted fashion, and we won't worry too much about the mechanism, but the alkene attacks one of the oxygens of the reagent, and then the other oxygen attacks the other side, so we get this cyclic osmate ester as an intermediate. That cyclic osmate ester is removed with sodium sulfate or sodium bisulfate to give the Syn or the cis diol. So in this case we have a ring, so this would be a cis diol with both of the bonds on the same side of the ring. Osmium tetraoxide is expensive and toxic, so it was discovered that we could use some co-oxidants like this NMO here or this alkyl peroxide as co-oxidants, so that we only need a small catalytic amount of the osmium tetraoxide in order to effect the reaction. So this is going to give a high yield of the Syn diol. We can also use potassium permanganate. Notice the similarity in structure between potassium permanganate and osmium tetraoxide. And it also goes through a similar concerted mechanism in order to obtain this intermediate, which this is a one-pot reaction, so this is not actually isolated, but we still get the Syn diol. But the synthetic utility of permanganate is limited because this potassium permanganate can react with a lot of other species, so we have to use the osmium reagent if potassium permanganate won't work. But again, the osmium is toxic and expensive, and so we try to avoid it by using potassium permanganate if possible. So let's see if we can predict some of these products for these reactions. Now remember, all of these, whether we're using the osmium species or the manganese species, the permanganate or the osmium tetraoxide, we're going to get what? We're adding OH and OH across a double bond, and we're adding that in Syn fashion. So the regiochemistry doesn't matter. OH is going to each side of the double bond, but they're going to be added to the same side because they're added in that concerted mechanism. So they're going to add to the same face of the double bond. So for A here, our product would be, if we have an OH on a dash, we're going to have the other OH is also going to be on a dash plus EN. Okay, for B, we've got OH on a dash, and the other OH would also be on a dash, but that doesn't matter because it's not a chiral center formed on the second one. So is that first one a chiral center? Yes, it is. So we say plus EN. So C, we've got OH and OH, either wedges or dashes. But if we draw the other one in, you can see that these are the same product, in fact, and so therefore we only need to draw one of them. For D, we have, let's see, an OH here, and let's just put this one on a wedge, and that's not a chiral center, so that'll be our only product. All right, thanks for watching. I'll see you in the next video.